Hello, this is week two's first lesson going over linear functions. So just consider the following functions. L of x equals mx plus b, or more commonly seen, y equals mx plus b. These are known as linear functions. When your constants m and b will be given, they will tell you your function's behavior. The m value will give you the slope. The b value will give you what's called the y-intercept. All of these linear functions form on a graph what is known as a line. So it'll just be a straight line. Your end behavior is what's happening to that line as your x values go to negative infinity or positive infinity. And we will actually look at this in Desmos in a separate video, as we have a separate example for this set of notes. So hold on to this for just a second. In these equations, m is your slope, b is your y-intercept, or where you hit the y-axis. And in the form L of x or y equals mx plus b, this is called the slope-intercept form, the most common type of equation you'll see, or form for a linear equation that you'll see. Let's go over the slope part now. The slope just measures the steepness of a line. And to show this, we've got two sort of accounts that are either gaining or losing money from week to week. And what we're going to do is we're going to find the average rate of change for each account after so many weeks. So in account 1, in between week 1 and 2, we're going to look at what's happening. If we look at week 1 and week 2 for account 1, we'll notice that we go from $2,000 to $1,500. So that's a decrease of $500. Our rate of change would be negative 500, but let's go over the formula for that. So what you would have to do is take your ending amount of money and subtract your starting amount of money. So 1,500 minus 2,000. And then divide by however much time has passed. In this case, we've gone 1 week. So we'll divide by 1. If we do this, we end up with negative 500 divided by 1, or just negative 500. That is our rate of change. Account 2, we will do something very similar. So our ending price minus our starting price. So 8,250 minus 7,500 divided by however much time has passed, which in this case, it's still 1 week. And this should just give us 750. All right. Next up, what we have is the time in between weeks 1 and 3. So in account number 1, go from $2,000, and in week 3, we're at 1,250. So 1,250 minus 2,000. In this specific example, instead of going for just 1 week, we actually pass 2 weeks. And so what we would do is we would divide by 2 instead of 1. Another way to look at this denominator is you have week 3 minus week 1, or 3 minus 1. This gives us negative 750 divided by 2. If we were to work this out, this should turn into negative 375. Essentially what this is saying is every single week in this account, we're losing $375. That's our rate of change if we're just looking at week 1 and week 3. We'll do the same thing for account 2. We have $9,000 minus 7,500 divided by, and again, it's the same period of time, 2 weeks. This also gives us $750. So it looks like the second account is pretty constant so far, just increasing by $750 per week. Let's look at the final weeks. So week 4, it actually looks like account number 1 had an increase in money. So we have $2,900. So between weeks 1 and 4, minus $2,000 divided by, we passed 3 weeks. So it would be 4 minus 1, just 3. So this should give us 900 divided by 3, or just 300. All right, what this 300 means is that if we didn't know these two values right here and we just knew the first and last value, our slope or our rate of change would be $300 per week, or plus $300 per week. So we go from week 1 to week 4. Every single week in this hypothetical, if we didn't know these values, we could assume them to be, plus 300, plus 300, plus 300. So 2,300, 2,600, 2,900. That is the slope or rate of change between these 2 weeks. Doing the same thing for account 2. Your final amount of money minus your initial amount of money divided by 3. We are running out of space here. Let's see. So I'm going to give you 2150. This will also give you 750. All right, so it looks like this one, account number 2, is pretty constant, as your rate of change is the same for every single week. So plus 750, plus 750, plus 750. And we can see that here, plus 750, plus 750, plus 750. Looking at this next part. So account 1 had a rate of change. This rate of change actually increased. So from first week to second week, it was negative 500. First week to third week, negative 375. And then first week to the last week, or the fourth, was 300. So this increases. And we'll talk about increasing rate of change a little bit later in this, well, not this unit, but a future unit. Account 2 is constant. The specific formula, or the more commonly seen in algebra classes formula for rate of change, is this right here, the y2 minus y1 over x2 minus x1, which is really what we were doing. And if we look at week 1 to week 3, y2 be this output, y1 this output, 1,250 minus 2,000. x2, x1, 3 minus 1, that gives us our denominator. So that's exactly what we were using here. This is pretty much your rise over run, and we'll go over this in a second. All right. So x1 and x2 are weeks, and therefore they are the independent variable. What we have right here is each account plotted on a graph in Desmos. This does skip a little bit. This is 1. This is 3. These are going up in increments of 1,000. So in week 1, looks like this account's number 1 had $2,000 in it. Account number 2 had 7,500. That matches perfectly with what we just saw. In order to find slope on a graph, what you will have to do is form a triangle between 2 points. And you will need to find the height and the length of the triangle. Let's look at the first 2 points. So account 1 is in red. Let's just look at account number 1. So if we're going from points 1 to points 2, so 1 week to 2 weeks, if we just draw a straight line from here to here, we can't quite tell what's going on here. What we need to do is find the length along with the heights of a triangle between here. So if we find the length, this is just 1 unit. This is 1. If we want the heights, we actually have to do this output right here, so the 1,500, 2,000, we have to subtract these two values. And again, I knew these values were specifically this because this is what our problem told us before. So our heights, again, as crazy as this scaling looks, would be 500. All right, so height of our triangle in this case be 500, length will be 1. All right. Next up, count 1 is not linear, so slope doesn't make sense. Yeah, so if we were to continue this trend right here of having a negative 500 slope, we would end up having a line that looks like this, which would not make very much sense to model this data. However, if we were to do this for account number 2, we're going to draw a straight line and it continues going through these points, this would model the data perfectly. All right, so let's look at account 1. So between weeks 1 and 2 for account number 1, our slope was negative 500. We just saw this. Oh, let me go over this a little bit more actually. So to find the length of this line right here, we can use Pythagorean theorem. We don't necessarily need that. This will be helpful in the future. For now, what we're going to do is we're going to look at the slope. The slope will just be however far we go up or down. In this case, we go down 500, so it'll be negative 500. Divided by however far we go left to right. In this case, we're going left to right 1 unit, so divided by positive 1. Our slope is just negative 500, which is the same thing as we found up here in this chaos. Between weeks 2 and 3, if we were to follow this same logic, again, you could make a new triangle. I'll go ahead and tell you that your height will be negative 750, or will be 750, and since we're going down, it'll be negative 750. Our length will be just 2 units. It'll be the same thing as what we found up here. So our slope here will be negative 375. All right, next up. Oh, this is in between 2 and 4. Let me clear this. Sorry about that. All right, adjust that. So if we were to look between 2 and 3, okay, it'll be the same math, but your line will be slightly different. Oh, that's week 1, so 2 and 3. Here we go. So our length is still 1, but our heights will be slightly different. So between weeks 2 and 3, we're going from 1,500 to 1,250. So this will be a 250 units decrease. So our slope will be negative 250 divided by 1, or just negative 250. So that is our slope between weeks 2 and 3. Next up, we want to find the slope between weeks 2 and 4. So let's do that. So we start out at week 2 and go up to week 4. This actually has a positive slope. So instead of having a negative number, we'll have a positive number here. So let's figure out how far we go to the right, how far we go up. So our length and our height. So our length should be 2 units. Our heights from here to here, again, it's hard for me to see some of these, so I'm going to check back on this. Week 2 should be 1,500. This should be 2,900. This would be 2,900. Just plugging into the formula, 2,900 minus 1,500, all divided by 4 minus 2. This will give us 1,400 divided by 2, or 700. All right, so this will be a positive rate of change between this last point versus a negative rate of change between these 2 points. You can use this same formula for the first 2 values. It'll give you the same thing. All right. Next up, if your slope is greater than 0, then your line is increasing. All right, so as x goes to infinity, so your x-axis, these values right here, as they go to infinity or far to the right, L of x, or your outputs, your y's, also go to infinity. Just saying, as you're going to infinity in this direction, you're also going to infinity on your y-axis. Your domain, again, all lines have a domain from negative infinity to infinity. Same thing with your range, negative infinity to infinity. If this line were to continue, we can see that we would cover every single x value, and there's no issues with division or square root of a negative number. Same thing out in the negative direction. So we will go forever in the x-axis, forever in the y-axis. Our in behavior, so to define each one of these lines, as x approaches infinity, L of x also approaches infinity. What this means is as your x values, this is the x-axis, as x values go to infinity, y values also go up to infinity. As x goes to negative infinity, so approaches negative infinity, or as we go to the left on the x-axis, our y values also decrease or fall down to negative infinity. Let's put a comma here to separate these. L of x goes to negative infinity. So this is for a positive slope when your line is increasing. If m is less than 0, so if m is a negative number, for example, y equals negative 7x plus 2, your line will be decreasing. Your domain is still the same. Domain for every line is negative infinity to infinity. Same thing with the range, negative infinity to infinity. There's no holes in our graph, there's no asymptotes, there's no problems whatsoever with linear equations. In behavior will be sort of the opposite of what you had when we had a positive slope. So again, this is our x-axis, this is our y-axis. For in behavior, as x goes to infinity, we want to know what's happening as we go to the right on our graph. Well, our line is decreasing. So as we go to the right, y goes down. So as x approaches infinity, L of x, or y, approaches negative infinity. Sort of running out of space here with the graph. That's all right. Next up, so we figured out what happens as we go to positive infinity. What happens as x goes to negative infinity now? So as x goes to negative infinity, L of x, or our y values, let me put commas again. So it's looking like as we're going out to negative infinity in this left direction, we're going to positive infinity in our y-axis, or on our y-axis. So x approaches infinity. And this happens for each one of these graphs. All of these have a negative slope. As we go to the right, the line goes down. As we go to the left, the line goes up. All right. Following, k is a real number, not equal to 0. So if m is 0 over k, so your slope is 0, what you have is just a constant line, or L of x is constant. All right, so L of x equals mx plus b. If m is 0, then 0 times x, this just disappears. All we end up with is b by itself. or y equals b. Again, you'll commonly see y equals some number as well. In this example, we'll have negative infinity to infinity as our domain. And then our range does change a little bit. So we don't increase or decrease at all. So again, domain for every line is the same, negative infinity to infinity, but the range here is just b. That's it. The only value we have for our range is whatever value is here. So in this case, it looks like 1.2. Our range would just be 1.2. If m is k over 0, this is actually not a function. So I guess we can technically graph it and we can consider it a line. It changes the domain. Let's actually go over this. So m equals k over 0. So you're dividing by 0. M is undefined. We don't have a slope. Sometimes, depending on your course, people will say it's infinite, but in this course, we'll say it's undefined. This results in a vertical line. All right, so yeah, this is not a function. It can't be written in our normal function way. However, we can still graph this. So instead of y equals b, you actually won't have a y value at all. You'll just have x equals some number. So right here, x equals a. Again, a could be 1, 2, 3, 4, 5, whatever your heart desires. Your domain is just a. Your range will be negative infinity to infinity. All right, so let's look at end behavior for both of these types of graphs. So for graph number 1, as x approaches infinity, so again, as x goes to the right, L of x, it just equals whatever your b value is. In this case, it looks like 1.2. L of x just equals b. And then as x approaches negative infinity, so as we go to the left on our graph, it's the same thing. L of x equals b. That's it. All right, end behavior for this one is a bit trickier to define. Because if we go as x approaches infinity, well, your function's undefined. Nothing's happening here. So as x approaches negative infinity, same thing. Your function's, again, not doing anything. It's staying at this value right here. We can't define this end behavior in a normal way. So normally we would do as x goes to infinity, what's happening to L of x? As x goes to negative infinity, also what's happening to L of x? We can't do this here. What we're going to do is we're going to swap it up a little bit. We're going to flip the order. We don't normally do this, but since this is not a function, it changes things around. We'll say L of x, or as L of x approaches infinity. So again, normally you're not supposed to work with these, but you can write it this way. So as our y values go to infinity, well, x just equals whatever your value is, so a. In this case, looks like negative 2.3-ish. Looks like where we're hitting the x-axis. And same thing as L of x approaches negative infinity, x approaches, or x equals a. All right, let's look at these last examples. So number 1, h of x equals, is this part of the homework? Let me make sure I'm not giving y'all answers. No. I guess there was a little sneak peek of the answers there if you want to use those. Just make sure you're watching the videos. All right, the end behaviors on this one. So your slope of this line right here will just be the m value or whatever's in front of the x. So slope is negative 2. Our y-intercept, or our b value, is whatever is being added or subtracted. In this case, negative 41.3. this line has a negative slope, so it would be decreasing. All right, in behavior, again, this is where we would write the as x approaches infinity. I don't have room for that, so I'll just say it aloud. As x goes to infinity, this is a negative slope. It'll be similar to this example right here. As x goes to infinity, so as we go to the rights, our line will go down to negative infinity. As x goes to negative infinity, our line will go up to positive infinity. So this would be our end behavior for number 1. All right, number 2, slope 0, y-intercept of 0. This actually just doesn't exist. Well, I guess it technically does exist. It will be an equation. It'll just be L of x equals 0. It's going to be one of your axes. It's a constant. All right, so right here we had a vertical line. Here we go. So to follow this end behavior right here. Sorry, where's our horizontal line? We're good. This end behavior right here. It's just your b value will be 0. And so it'll just be your x-axis, pretty much. Just a line on the x-axis. X equals 10, this will be a vertical line. M is undefined. B, well, this is a vertical line and it's not on the y-axis. There is no y-intercept. All right, does not exist. We'll abbreviate, does not exist. It's not real. Lastly, we have a crazy looking function over here. And again, your end behavior will be this right here. All right, this will be a vertical line. Okay. Your last example here looks really crazy. Y equals pi over 4 times x. You've got to remember pi is just a constant number. It's 3.1415, yada, 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 yada. It's irrational, but it's still a constant. So our slope would actually be just pi over 4. This is just going to be a number. It'd be, I don't know, 0.76 something. Still a number. Our y-intercept here, we're not adding anything, but there is technically a plus 0. Our y-intercept will be 0. Pi divided by 4, well, pi is a positive number. 4 is a positive number. Positive divided by positive will be positive. So we will be increasing. Running out of space. And our end behavior will look like this right here. As you go to the right, your graph goes up. As you go to the left, your graph goes down. That'll be it for video number 1.